Okay, 5.1, derivatives of exponential functions. So what we have to do is we're looking at exponential functions with the Euler number e. E is approximately equal to 2.718. So Euler e is like pi, in which it is an irrational number and it belongs to the world of irrational numbers. It is a number that doesn't repeat, and it's a number that doesn't end. So 2.718 is an approximation. Now, if I give you y equals e to the x, and you want to find the derivative of y equals e to the x, now let's look at the graph. If you look at the graph, it looks very much like an exponential function, because remember, this is an exponential function. 0, 1 is the y-intercept, and at 1, the value is 1e, and you want to find the derivative of this. Well, the derivative of y equals e to the x is just going to be y prime is equal to e to the x. It's the same derivative. Now be careful. That only works if the exponent is just x. What happens if it isn't? So for example, in general, y equals e to the g, e to the power gx is equal, the derivative of that is equal to g prime of x times e to the gx. So again, we have that derivative where you take the derivative of this and it turns out to be that, but don't forget that the exponent is a function of x, so we need to take the derivative of that function of x. Very important to keep in mind. Now, example 1, you're asked to differentiate some functions here. So the first one is f of x is equal to e to the power of 5x. Well, the answer to that will be 5e to the 5x. Let's look at another one. Y equals x to the 6 times e to the 2x. What do we do here? Well, it's product rule, folks, and so you have to use the product rule, which is going to be y prime is equal to 6x to the power 5 times e to the 2x, so the derivative of the first times the second, plus the first times the derivative of the second, which is 2x to the 6, e to the 2x. Because the 2 and e to the 2x comes from the derivative of e to the 2x. X to the 6 was already there. And so this is the equation. Sometimes you may be asked to common factor. So you will have a common factor of 2x to the power 5, e to the 2x, and you're left with 3 plus x. Why you would do something like this is, for example, when you need to set the derivative equal to 0. Very important to a common factor. Makes life simple. Example number 2. Find the equation of the tangent to the curve y equals e to the negative 3x at a point x equals 2. How do we do that? Well, find the derivative first, and then what you do is you substitute the value for 2 for x, and you get the derivative is equal to y prime is equal to negative 3 e to the negative 6. Then you're going to sub the slope and a point into the equation, and turns out you end up with an equation that looks like this. Common factor e to the negative 6, and what that gives you is this value. This is the equation of the tangent line. Now, how did we get from here to here? That's usually what the question is asked. So a little example is shown beside there, where from here to here, you expand this out, you get, and then you bring this over. So y equals negative 3 e to the negative 6 x plus 6 e to the negative 6 plus e to the negative 6, and those two will combine to give us 7 e to the negative 6 and negative 3 e to the negative 6x. We take out the e to the negative 6, and you're left with negative 3x plus 7. All right, example number 3. Find the equation of the tangent to the curve y equals e to the x times e to the x squared at x equals 3. What do we do here? Well, folks, you need to before we take the derivative, we should probably use our exponential rules to simplify that first part. So y is equal to e to the x plus x squared. What does that mean? Well, now we can do the derivative. Y prime is equal to 1 plus 2x times e to the x plus x squared. After that, we plug in x equals 3, and we end up with 7e to the 12. To find the equation of the tangent, we sub this point 7e to the 12, that's your slope, and a point, which is 3, and plug in 3 for x in the original equation. You get e to the 12 into the equation, linear equation, and you get something that looks like this, expanded, collect like terms, and there's an example of what I skipped in red, is the part that I skipped to get from this line to this line. Here's the part that I skipped. All right, if you have any questions, please feel free to ask me. This is the end of this lesson. Have a numerical night.